we could well ask, how far did we travel along this curve between t equals 0 and t equals 2? The arc distance would be the integral from 0 to 2 with respect to t of the arc increment. Remember, the arc increment is ds dt, so we're integrating from 0 to 2, we're integrating ds dt with respect to t. What's ds dt? That's the rate at which position, distance along the curve is accumulated with respect to t. The key quantity there is how fast are we moving along the curve, so how far do we move in a time interval dt. Find a good place to draw this. Let's draw a tangent vector here. Okay, this could be our r of 1/2 vector. It's upward and forward, well, actually, in this direction. And I wrote that as r of t, I meant r prime. R prime of 1/2, that's our velocity vector. So that our rate of change of position, the rate at which we're accumulating distance is nothing but the velocity vector. So we're integrating the magnitude of the r prime of t vector with respect to t. That is, our ds dt, the rate at which we're covering distance, is the magnitude of the r prime of t vector. And r prime of t is just our velocity, so the magnitude of r prime of t is our speed. This integral is just an integral of speed with respect to time. Now the r prime of t vector has a magnitude, and we've actually calculated the magnitude both for this and for this. In the case of our first function, and I just noticed that I have a b here in front of the sign. Of course, if a and b are different, this curve becomes an ellipse, elongated in one direction or the other. I intended to have a here and a here, and the whole analysis has assumed that we have a cosine and a sine. So I'm going to have to go back and correct that, but you can be aware of that. Okay, I'm not going to correct that right now. Using a for both of these coefficients, if a equals b, then the r prime function for this curve, and I'll write that in the same color as I've used here, our arc distance becomes the integral from 0 to 2 of the square root of, now our r prime of t, we've calculated it, it's going to be pi a times the sine of at negative pi a times the sine of pi t, and pi a instead of b times the cosine of pi t, and 2t here, and we've seen that that's simply pi squared a squared plus 4t squared. We integrate that function, that magnitude of r prime of t, which is our ds dt, with respect to t, and we get the arc distance. Had we integrated for this function, our magnitude would just be, again, if a equals b or if b equals a, our magnitude here would just be pi a. We'd integrate pi a from 0 to 2, and we would get 2 pi a, which is the circumference of a circle of radius a. Your book has a formula for the arc length. If your r function is xi plus yj plus zk, then you're supposed to integrate the square root of dx dt squared plus dy dt squared plus dz dt squared with respect to t. But what is this? Well, this is just, for this function, it just gives us this. The dx dt is nothing but the magnitude of r prime of t. This expression, the dx dt squared plus dy dt squared plus dz dt squared, is just the derivative of r. If you take the derivative of r, you get x prime I, or dx dt I, and dy dt j, and dz dt k. The magnitude of that is just this, so that this formula would lead you to the same integral. But really, we probably want to think in terms of the geometric interpretation and the fact that the magnitude of r prime is the rate at which we're sweeping out distance or covering distance along this curve with respect to our parameter.